Hi, welcome back to my channel. Well, in this video, we'll learn how to perform the basic correlation and regression analysis of continuous variables in JASP. For that, I have already stored a data set in in a CSV format. So, how to perform? Let us click here on this main menu option. Then we will click on this open. Then we will click on this computer. Since my data set is on my desktop, we'll click on this desktop. The name of my data set is MLR. I will click on this open here. So our data set will get imported on my this JASP console. So we have 6 continuous variables. The first one is root yield, trimeter, number of leaves, shoot length, root length, and total cavity. This is the same data set which I have used to perform the correlation and regression analysis in one of my videos, but that was based on RStudio. Let us start with the correlation first. In order to perform the correlation analysis of these 6 continuous variables, we have to click on this regression here, and here we have 2 options, classical and Bayesian. We will click on this classical, and here in classical we click on this correlation. So how to perform? So we will take all these variables, we will highlight all these variables and put them into this dialog box. So within one click, we have a correlation matrix here. If I will take an example of root length versus root yield, so it has a positive correlation. Since this is a Pearson's correlation, why does Pearson? Because the variables are continuous. So by default, it takes Pearson's correlation into account. Otherwise, we have 2 options here, Spearman's and Kendall's correlation also. But these two are used when we have a data which is an ordinal or nominal scale, or we have a discrete type of variable. Since our variables are continuous, so that is why it has taken Pearson's by default. So this is a Pearson's correlation coefficient. If I will take an example of root yield versus root length, we have a positive correlation which is 0.75, and it is significant also. We have also another option. We can flag the significant correlation also here by means of these asterisk values. All these are quite significant figures here, and all these correlation values are above 0.5. And 0.5 is considered to be a good standard in statistics. Above zero point 0.5, they are considered to be a good amount of correlation, provided they are significant. So we have another option. We can display the confidence intervals of these correlation coefficients. Since if I will take an example of trimeter versus root yield, we have a negative correlation, and this correlation coefficient ranges from within this limit. It ranges from minus 0.6 to minus 0.8. This is a lower limit, and this is the upper limit of this 95% confidence interval. We have a very good option here. Instead of this a numerical type of a table, we can create a heat map. I think this is one of the beautiful options available in this JASP. So we have a heat map. We can create this heat map in RStudio also, although we have an option here we can customize these colors and also. But within one click, you will get the heat map displayed. If I will take an example of root yield with shoot length, we have a significant correlation, and that is 0.63. It is positive. So with the increase in shoot length, there's an increase in root yield also, and with the increase in total carotene, there's a decrease in with the increase in total carotene, and you will have a negative correlation in this. Now it depends upon, it makes sense as per the objectives of your study. So within 1 or 2 clicks, you can get this whole amount of information along with this beautiful data visualization. Now let us perform the regression, the basic regression. Again, we will click on the same. Then we will click on this linear regression. Then here we have options. Automatically this model summary, ANOVA and coefficients blank tables, they get displayed. Now how to perform? So here we have to choose our dependent variable. Suppose let us take this root yield as our dependent variable. Then let us take all these variables and treat them as our covariates here. Now we have the results in the form of a multiple regression. Since we have only one dependent variable, and we have almost 5 these explanatory variables. Here, in case of model summary, we have 2 options: null hypothesis and we have an alternative hypothesis. Let us see this. Since whenever we are performing any kind of a study, we have to propose or set a certain kind of a hypothesis, and after applying a proper statistical procedure, either we may agree with that statement or disagree with that statement. For that, we have to set a null hypothesis. is. So here you can find out this is a multiple correlation coefficient. This is a linear relation of all these variables with our response variable. It is 0.8, and we have this R square value, that is coefficient of determination, and it is 0.78. That means its range is from 0 to 1 or 0 to 100%. That means 78% of the variation on of this dependent variable is explained by all these five explanatory variables. And we have another option, that is adjusted R square. This is usually used for model comparisons when we have to compare different models with different parameters. And we have a selection criteria also here, that is root mean square, that is 0.62. So in case of ANOVA table, what we have a significant p-value, so we are good to go. This model is well fitted. We can say it because the p-value here is less than 0.05. And the good thing about is we have the options of unstandardized and standardized coefficients. And here with every increase of number of leaves, there's an increase in root yield by means of 0.24. So similarly, you can make the interpretation of the rest of the variables. Now, if we will go to this statistics here, we have a lot of options here. We have model fit, we can see, we have R square chain, we have descriptive study, we can perform the part and partial correlation, we can see the collinearity diagnostics also. See, we have eigenvalues, we have condition index, and we have variance proportions. By means of this, we can check whether there's an existence of multicollinearity or not. Then we have a lot of options in fact here. If we will go down here, we have model specifications also. Then we have options for these plots also. We can make plot that residuals versus dependent variables. You can see by means of this, you can check the assumptions of the model. We have another plot here, residuals versus predicted values, because uh, the main idea behind the implementation of this is to fit a functional relationship and to predict the future values also. Then we can make these Kyoto plots also. So we have a lot of options. So within few clicks, you can get a huge amount of information. So this again, this statistical package is highly recommended to the scholars who want to perform or this type of an analysis. In next video, we'll make a detailed video in context the analysis of multiple linear regression, how we can check the collinearity diagnostics, what is stepward and backward method, like we have here the option, the model specifications, how we can choose which of the important explanatory variables are important, because in this case we have a 78% of the variation explained by all these variables, but all these variables might not have a significant effect on our response value. So how to choose, how to see these this diagnostics in next video. I will make a detailed video in the next video. So thank you very much. Hope you will like.